Well, welcome back, everyone. I'd like to shift gears a little bit. I've been talking about screening up to now this week, and screening does involve the notion of prediction. We're trying to classify people as likely or not unlikely to have a disease based on a screening test. Well, now I want to extend the idea of prediction to talk about more formal clinical prediction rules that try to estimate a person's risk of developing some outcome in the future. To do that, first let me take a step back to last week's lectures when we talked about regression models being used in epidemiology. And at that time I said there are two main reasons why we epidemiologists use regression models. Last week we talked about the main reason, the idea of controlling confounding. I tried to set the big picture message that when you build a regression model and you look at the coefficient of one of your risk factors in that regression model, that regression coefficient is estimating the effect of the association between that risk factor and the outcome, controlling for all the other risk factors in the model, controlling for the potential confounders that you've included in the model. And we went through a series of analyses where we looked at using regression models to estimate the effect of being prescribed to take blood pressure medications among people who have been diagnosed previously with hypertension on the outcome of dying in 24 years of follow-up. Well, this week I want to switch gears a bit. I want to still talk about regression and regression models in epidemiology, but now for a different purpose. A purpose that doesn't focus on one risk factor, one exposure, like taking blood pressure medications and its effect on your outcome, but really looking at a series of risk factors and combining them some way to predict an outcome. We want to predict a person's risk of developing an outcome like coronary heart disease in the next 10 years based on their age, their sex, their smoking status, their cholesterol levels, their blood pressure levels, what have you. So now the purpose is to provide an estimate of the risk of developing an outcome. Not a risk ratio, not an odds ratio, but an individual person's risk. Estimating whether your risk is 20% or 80% or 90% of developing some outcome, basing that risk estimate on many risk factors, combining them into a regression model. So the output of this regression model is not going to be a risk ratio or an odds ratio, it's going to be a predicted risk. So let me first talk about how you decide what variables to put into a regression model if you're doing research involving epidemiology. And the big message I want you to take home is that, in my opinion, the decision to put risk factors into a model or not put risk factors into a model in part depends on the purpose of the model. Last week, if the purpose is to control confounding, we want to know whether people who are given blood pressure medications are at higher risk or lower risk of dying compared to people who are not giving blood pressure medications, and we want to control for 5, 6, 7, or 8 factors. The main aim of the analysis is to control for all the confounding. Let's think about it. If you had done a study and you think you have confounding by 5 potential factors, age, sex, blood pressure, cholesterol, and say history of coronary heart disease, you cannot write a paper where you just control for 3 of those and not the other 2, saying that you didn't have time or you didn't have the energy or whatever the resources you needed to control for all 5. You cannot present a result in a paper that you think is wrong, is still confounded by other factors. To the best of your ability, you have to control for all the confounding that's connected to all the potential confounders in your analysis, not just a subset of them. And typically what that requires is that you have to include in your model terms for each of the confounders. So if you looked at the exercises we did last week, we had in the model a term for age, a term for sex, a term for blood pressure, actually 2 terms, one for systolic, one for diastolic. We included another term for total cholesterol, another term for diabetes, another term for smoking, overweight and obesity, etc. So typically if you have multiple confounders that you feel you have to control for, typically you have to include all of them in your model as potential risk factors. Now there is a potential alternative. You might only have to include a subset of those risk factors when those risk factors are correlated. If you're controlling for age and sex, you might be indirectly controlling for other factors that are highly correlated with age and sex. If you're controlling for systolic blood pressure, you might not also need to control for diastolic blood pressure. So there's a possibility, if your potential confounders are correlated, you might be able to just control for a subset of those larger set of potential confounders and indirectly be controlling for the other ones. But generally speaking, if you have 5, 6, 7 potential confounders that you have the need to feel you have to control for, then generally speaking, you include terms for each of those potential confounders in the model. The problem is you don't want to be criticized for not controlling for, say, blood pressure if you didn't include it in the model. You publish a result. You show that people who received antihypertension medications had a different risk than people who did, odds ratio equal to 1.4. Someone looks at your paper, notices in the paper you didn't control for age. They're going to write a letter to the editor saying, interesting paper by Dr. Cook, but I disagree with his findings because they might be confounded by age, because I saw that he did not include age in his model, and everyone suspects that age might be a potential confounder that's needed to be adjusted for. So in practice, the motivation is to be liberal, to include enough factors in the model that you need to control for the aggregate or all the confounding. And if you have 10 potential confounders, that usually means you have to include all 10 factors. Because what you want to have is a model and an analysis that has face validity. So when someone looks at your results, looks at your tables and your manuscripts, sees what you've controlled for, they say to themselves, yeah, he controlled for everything that I think needs to be controlled for. Therefore, I believe his result. It looks valid. On the face level, looking at his paper, it looks like he's controlled for all the confounding. So if the purpose of building a regression model is to control for confounding, that was last week's exercise, typically you want to build big models that control for each individual potential confounder. But this week, if the purpose is to build a prediction rule, realize the purpose of your prediction rule is to apply it to the next person who comes into your office. If you're building a model to predict a person's risk of developing heart disease in the next 10 years, you have this data set you've been collecting on people with all these risk factors and the outcomes, whether they did or did not develop heart disease after 10 years of follow-up. You build a prediction rule, as we will talk about in these lectures, that provides a formula, a prediction rule for predicting a person's risk of developing heart disease. What you're going to be doing with that prediction rule is applying it to your future patients. When someone comes into your office and you record their information about their age, their sex, their smoking habits, their cholesterol levels, their blood pressure levels, etc., and plug that person's risk factor profile into your formula, into your clinical prediction rule, and it says that that person's risk is 40% chances of developing heart disease in the next 10 years, realize you're going to be treating a person in a certain way based on what that value is for that estimated risk. So prediction rules are developed for the purpose of applying them for future people, future data, with the aim of trying to identify high-risk people versus low-risk people that might be treated differently in their medical practice. Well, the motivation is not to be liberal, but to be parsimonious. We don't want to build very, very, very big models. We want to build a simpler model. It usually means a smaller model, because simple models tend to generalize better than other models. If I have a data set from which I'm building my prediction rule, and I can look in that data set and look at all the risk factors that I suspect might cause this outcome, coronary heart disease, develop. I might look at other factors which I'm not sure whether they should be risk factors and let the data decide whether there's evidence there that this factor is related to the outcome. The more I look into a data, the more idiosyncrasies I'll find. Factors that are associated in this data set with the outcome that are not going to be associated with other data sets, with other people. It just might happen by chance that in this data set, that people who lived on the right-hand side of the street were more likely to develop heart disease than people who lived on the left-hand side of the street, due to the selection of people who came into this study. That doesn't mean that in future people living on the right-hand side of the street is increasing your risk of getting heart disease. But if I included in my prediction rule that factor, living on the right-hand side of the street, I might be building a prediction rule that works very well in this data set from which I'm building the rule, but it's not going to generalize very well to other data sets. That's referred to as overfitting or overtraining in the model building process. I went too deeply into my data set, found associations in this data set that hold true in this data set, but are not going to be generalizable to other data sets. So the bigger model, the more complicated model, that include these idiosyncrasies, these non-generalizable factors, is not going to hold up very well in future data sets. So unlike the motivation for controlling for confounding with the regression model that says be liberal, make sure you control for all the confounders, when you're building a prediction rule, we want something that's going to perform well in other data sets, and usually that what means is smaller models, simpler models are going to perform better in other data sets than more complicated models. So the motivation, the driving forces to decide what to include or not to include in a regression model in part depends on the purpose of the model. Controlling confounding usually leads to big models. Building prediction rule usually leads to smaller models. So with that in mind, let me give you an example of a regression model that was used as a prediction rule. This is a model for something called the mortality prediction model. Actually, there's a series of models, different variations of the mortality prediction model. I give you the reference on the bottom of the slide. Essentially what it is, it's a model that's going to predict your chances of surviving a hospital stay. The motivation behind this prediction rule was to look at people who were being hospitalized and being assigned to an intensive care unit. And what they wanted to do was come up with a measure of disease severity. How sick is this person who's being admitted to this intensive care unit? So they can decide which patients receive more careful monitoring, more detailed teaching than other patients. So what they chose as their measure of severity was the risk of dying in your hospital based on measurable risk factors. So what they had was a large data set, people admitted to this one hospital. They collected a large amount of information of potential risk factors that might predict a person's risk of dying in the hospital. They had the outcomes, what actually happened to those people, whether they died or didn't die in the hospital, and they built a logistic regression model using only the predictors that they thought were the important ones, the ones that are going to be generalizable to other data sets. And they ended up using just the following predictors in their final prediction rule. Now, these were not the full set of potential predictors they started with. These were the ones that they selected from a larger pool of potential predictors to be the ones that they wanted to include in their final model. So they went through a series of model building steps, trying to identify the most important risk factors that best predict the outcome, mortality, in this data set, and are more likely to be generalizable, hold true in other data sets. So the final risk factors were the following. They had a binary risk factor, which is the patient's level of consciousness, coded as 1 or 0. 1 if the patient was essentially comatose, 0 otherwise. They had another risk factor, which was the reason for the admission, the type of admission. Was this an emergent admission to the hospital, or was this an elective admission? In other words, if someone was scheduled for surgery, and that surgery routinely meant that you went to the intensive care unit after finishing the surgery, that would be an example of an elective admission. It was planned. An emergent admission means that something went wrong. You might have had chest pain, a heart attack, and they rushed you to the hospital. Another risk factor is whether a person had been diagnosed with cancer. Cancer was part of the reason for the person being in the hospital. Another one is whether the person went through prior CPR, whether that person had to be resuscitated in the past, yes or no. Another one is whether the person was suffering from an infection in the hospital. That was the reason they're being sent to the intensive care unit. Those 5 risk factors are all binary, 1 if yes, 0 if no. In addition to that, they had the age of the individual measured in years, and also the blood pressure of the individual. And in the model, they included not just the blood pressure, but the square of the blood pressure also. Now, last week I was talking about the importance of model assumptions. That when you build a model, you want the model to be valid. You want the way the model is constructed to really reflect truth. Well, notice what they have in the model is both blood pressure and blood pressure squared. If you remember back to your high school days when you learned about different types of relationships between x's and y's. We talked about a straight line relationship before that says y is equal to mx plus b. That means that there's a linear straight line relationship between the value x and the value y. So for age, for example, when it's included in their final model, they're assuming a linear relationship between age and your risk of dying in the hospital. That the older a person becomes, the higher the risk is of dying, which seems to make sense based on prior knowledge. But what's the relationship you'd expect between blood pressure and, say, your risk of dying in a hospital? Now, blood pressure, we all know that very high blood pressure is not a very good thing to have. Hypertension. People with hypertension, very high blood pressure, are at increased risk of dying. But also people with very, very low blood pressure, hypotension, are also at very high risk of dying. So the relationship between blood pressure and maybe your risk of dying is not a straight line, but a curved line. It might look something like this. It might have a J-shaped relationship, where high blood pressure brings with it high risk of disease, low blood pressure brings with it high risk of disease. Well, how do you represent a curve like that in a regression model? Well, going back to your high school days, the equation is something called a quadratic equation that says y equals a plus b times x plus c times x squared. That's how you'd represent a curved, or what we call a quadratic relationship. So when they built the model, they anticipated, and the data supported it, that blood pressure would not have a linear relationship, it would have a quadratic relationship. So when they fit their model, their final model, their prediction, well, they got the following equation. Let P be the risk of dying in the hospital. They used a logistic regression model, like we talked about last week. Log odds of dying in the hospital is equal to the following formula. It's equal to minus 1.37 plus 2.44 times whether you're comatose or not, plus 1.88 times whether you have an emergent or elective admission or not, plus going down the line 0.0368 times your age, assuming a linear relationship between age and your log odds of dying, minus 0.0606 times your blood pressure, and then a plus 0.0017 times the square of your blood pressure, assuming a quadratic relationship. That's what their final model looked like. And this was only developed after a series of model building steps. This was not the initial model they built. This was the best model that they built that they feel holds true in this data set and also will be generalizable to other data sets. So how do we use it on a future person? A future person comes into your hospital, you ask them or you measure their values for these risk factors, and you just plug their values into this equation. And what you'll have on the right-hand side, after you do all the multiplication and all the addition, is an estimate for that person's log odds of dying in the hospital. So for example, if you have a patient coming into your hospital who's not in coma, who does have cancer, it's an elective admission, no prior CPR, no infection, say is 50 years old and has a blood pressure of 120, that means his blood pressure squared is 120 times 120, then what you'll do is fill in each of these holes the values for the risk factors in the previous equation. So if I go back to the previous slide, if you are there for not being comatose, you put a 0 in for there. If you are 50 years old, you put a 50 in for age. If your blood pressure is 120, you put a 120 in for the blood pressure. And for blood pressure squared, you put 120 squared in for that. So what you do is you fill in to this formula the values for each patient's risk factors as they enroll into your hospital. And if you do that, you'll get the bottom part of the equation. If you do all the arithmetic correctly, and hopefully I did that, you'll get a final value of minus 2.7 for that person's log odds of dying in the hospital. Well, if their log odds is equal to 2.79, is that the right value we have over there? Yes, that means if the log odds is minus 2.79, that means the odds is e to the minus 2.79. That's about 0.061 or something like that. That means your risk. Remember, the relationship between risks and odds is risk is equal to odds over 1 plus odds. So it would be 0.061 divided by 1.061. If you do the arithmetic, that to 2 decimal places would give you the risk of 0.06. So what this prediction rule allows you is for any patient who comes into your prediction rule is to take his risk factors, plug them into this formula for this clinical prediction rule, and out will pop that person's predicted risk of dying in the hospital. And you can determine whether this person has a high risk, in which case you could say he's severely ill and demands more monitoring, or low risk, in which case he deserves maybe less monitoring. It can be used as a severity of illness measure. So I'll get back to this example a couple of times when we talk about how you evaluate the performance of a prediction rule, but essentially that's what's happening here. We're building a model, a regression model, not for the purpose of talking about the effect of one risk factor controlling for confounding. There's no exposure here, there's no confounders. All these factors are equally important to us. We're just combining them together to give us an estimate of a person's risk of developing an outcome. Well, the next time we meet, I want to talk about how we evaluate whether this is a good prediction rule or a bad prediction rule. So that's what we'll talk about next time, and I'll see you then.